Good morning, everyone. My name is Bharat, and welcome to today's seminar series for eupraxia. Our today's speaker is Professor Enrica Chiadroni, and she's an associate professor at Sapienza University of Rome. And she has spent 2 decades at the INFN laboratory, where she was part of the Spark Lab group. In today's talk, she would talk about the multidisciplinary application of plasma-based accelerators, which would cover, different applications of plasma accelerators ranging from medical imaging to material science. So before I give the presentation to Enrica, everyone who is attending online, just want to tell you that if you have any question, you can put it in the chat, and then at the end of the presentation, we would discuss the questions at the end. So, yeah. So, Enrica, whenever you are ready, you can share the screen. You have already shared it, but you can start the presentation.
So, good morning, everybody. It is my pleasure to present here part of the work we are doing, and also an overview of the work many groups in the world are doing concerning the applications of plasma-based accelerators. So I would provide a brief introduction to plasma accelerators, in particular highlighting the figure of merits of plasma accelerators and how these each quantity has been optimized in order to be used, and in order to let plasma accelerators used for applications. And I will then give an overview of the several applications of plasma-based accelerators, not only radiation sources, in particular free electron lasers, but also other kind of applications which are worth to mention as a wide range of expectations from these novel accelerating techniques. So, based on the kind of plasma accelerator we are considering, so either in case of laser driven or particle driven, the ponderomotive force in case of laser driven or the space charge force in case of particle driven keeps pushing electrons away, which set a charge separation, which is a setting which is source of an electric field. So ions, which are heavier than electrons, pull back electrons in a time scale which is in the order of 10⁻100 femtoseconds, and this allows for a ultra high axial electric fields settings to co-propagating with laser at the velocity which is c or close to c. This allows for increasing the accelerating gradient from the level of conventional structures, which is less than 100 megavolt per meter, up to the plasma structures, which can sustain accelerating gradient in the order of 100 gigavolt per meter, so less than 100 gigavolt per meter. This would allow for the shrinking of the plasma accelerating module, and in principle allowing for and is what is all our efforts are focused to shrink the dimension, the footprint of the accelerator. So if we think to the slack accelerator, which is providing 10 GeV electrons in 1 kilometers, in the future, in the next future, with the eupraxia plasma-based facility, we plan to have 1 GeV in 40 centimeters. So what are the figures of merit of this kind of any kind of accelerators, but those which are needed to be optimized in order to be used, in order to let these kind of accelerators used as a user facility, so for applications. As first, of course, the total energy gain, which means a high gradient, which is naturally obtained in plasma-based accelerators. Then there are issues on the quality, in particular emittance, energy spread, and depending on the application, brightness and luminosity. The control of these parameters, so the stability of the acceleration, the reliability, the tunability, and the control of jitters, of any kind of jitters. And finally, but not really, but last but not least, the amount of charge we can deliver to the applications and the repetition rate. So depending on the applications, we might be interested in optimizing luminosity in case of high energy physics applications, or brightness in case of radiation sources or advanced radiation sources. And these two quantities can be related to the machine parameters, so can be related to the number of particles per pulse, the repetition rate. In particular, for high luminosity, we need small spot size, which means low emittance. In case of high brightness, we need to keep under control the length, the pulse length, and the energy spread beyond the transverse emittance, which must be preserved and must be below a certain level. So, toward applications, a lot of efforts have been done in order to demonstrate the multi-GB acceleration, and this is, as we will see in a few moments, this has been established. But what is also important is to accelerate high quality electron beams in centimeter scale, or in a smaller footprint, smaller plasma structures. Beyond the plasma accelerating module, what is of interest is to control the injection and the matching to the plasma accelerating module, because this would allow for a better control of the emittance and would prevent from emittance growth in the following step of the acceleration. So, depending on the regime, and in particular on the blowout regime, we have to preserve, to keep this matching condition on the beta twist parameter. And for typical parameters, which can be gamma of 1000, and for plasma density of 10 to 16 centimeter to -3, we need to have a beta matching, which translates in a transverse beam size matching in the order of micrometers. Another issue is encountered in terms of extraction of the electron beam from the plasma accelerating module, because not only the accelerating fields, the longitudinal fields are stronger than in conventional accelerators, but also the focusing fields are stronger than conventional accelerators. And this would result in a huge transverse size variation of the beam when propagating from the plasma outer surface to the conventional focusing, which is needed to deliver the particle beam down to the applications. And this, exiting from the plasma accelerating module, we need to handle with beams which are of micrometer size and with a huge divergence in the order of milliradians. And of course, these put an issue on the quality which can be preserved, because these very large angular divergence, together with a large energy spread, would result in a strong degradation of the emittance, which is usually not wanted for any kind of applications. So one possibility to control injection and extraction is to consider an integration of two active plasma lenses together with the plasma accelerating module, in order to smoothly inject and preserve the matching condition, accelerate and smoothly extract the particle beam, in order to keep under control the beam size and then the emittance. In this experiment, we have demonstrated to be able to control the emittance growth, but of course this has been still implemented and still improved in order to completely preserve the emittance. But this can be a solution in order to go beyond the miniaturization and the development of next generation tabletop machines. In terms of high gradients for laser plasma acceleration, numerous experiments have demonstrated over the past year peak acceleration larger than 100 GeV per meter, but with a limited total energy gain. In this experiment, by using a dual laser and a channel-guided plasma to sustain a ultra-high accelerating gradient, the 10 GeV electron beams has been achieved in 30 centimeter acceleration length by using 20 joule laser energy. Concerning the particle-driven wave-field acceleration, in this experiment has been demonstrated an energy transformer ratio larger than 2 to boost the acceleration efficiency. So injected and accelerated electrons up to 25 GeV has been demonstrated in a 2.5 meters plasma structures, also preserving the quality of the beam, so with a less than 1% RMS energy spread. In terms of quality, a lot of experiments have demonstrated the possibility to preserve the energy spread. In particular, in this experiment here, it has been demonstrated that the optimal beam load in the nonlinear regime, where the wave field has been flattened at few percent here. In this second experiment, it has, by setting a positive chirp in the witness bunch, the longitudinal phase space rotation has been observed during acceleration, and which has demonstrated to control the energy spread, and actually not also to preserve it, but even to improve it with respect to the injection, so to keep energy spread below the value at injection in the plasma. In terms of transverse beam quality, so also the transverse emittance preservation has been demonstrated with these direct measurements performed at flash forward, considering a kind of quadruple scan technique, where in this case the scan was done on the object plane to measure the evolution of beam size in case of plasma cell extracted, and with a plasma cell injected in order to then get an envelope in order to understand what was going on in the plasma cell. And this experiment has demonstrated the overall quality of the electron beam, not only for the transverse emittance, but also preserving the energy spread with a quite good propagation of transport of charge. Also, the slice emittance preservation has been measured and to be kept below 0.7 millirad. In terms of stability, this long-term stability of laser plasma acceleration is now well established, resulting in a 24-hour continuous running, which has enabled the development of novel techniques, in particular this active energy compression, to reduce the central energy jitter and the RMS energy spread below 0.1%. Also, the stability, again, other sources of instability and jitters can be found in the variation in the drive laser. And in this particular experiment for the single cycle laser drivers, by controlling the carrier envelope phase, it was possible to change in the pointing of the electron beam as it is shown here in these images, where the numbers are related to this red curve, where by changing the carrier envelope phase, it was possible to adapt and to adjust the pointing of the electron beam. And this effect could be used to control the injection of ultra-short electron bunches in laser wave field accelerators. And together with longitudinal focal stabilization, it was possible to reduce the electron beam jitter. In terms of plasma source, for the particle-driven case, we have studied for the Eupraxia Spark Lab project, we have studied and measured the stability of the plasma formation from the 3 centimeter long capillary up to the 60 centimeter long capillary prototype, which will be used in the Eupraxia Spark Lab project, and this stability has been measured up to 1%. In case of the throughput efforts, which needs to control the transport of charge and also the repetition rate, in order to increase the repetition rate, which is always demanding from the point of view of application, so from the point of view of users. In case of laser plasma accelerators, the limitation is given by laser technology, and for TIE Sapphire, which is the dominant format in this kind of experiments, we are near to its ultimate limit because of the energy efficiency. So there are there is a lot of efforts. So several groups are working on improving the efficiency, the average, and the energy efficiency, in particular by using these high average power fiber lasers. In terms of repetition rate, there are also from the plasma point of view, there have been several experiments which have demonstrated that the plasma is able to recover at nanosecond time scale, enabling the operation of plasma wave field acceleration at very large repetition rate. There are mainly two experiments which have demonstrated this nanosecond time scale recombination of the plasma, in particular by by studying the ion motion. What is still a technological challenge is the fact that is also the plasma source must sustain high repetition rate, and in this regard great efforts are ongoing in Frascati lab for the Eupraxia Spark Lab project in order to demonstrate the possibility to run plasma module at high repetition rate, because several issues might prevent this, in particular the slow valve activation, for which then continuous injection of plasma is needed, the overheating of vacuum pumps, for which water cooling system must be provided, and also the overheating of the high voltage pulsar circuit, for which an air cooling system must be integrated in order to allow for high repetition rate. And you can see, and last but not least, also the capillary erosion because of the high number of shots. You can see here a picture of the high voltage pulse circuits, and in particular how these the most delicate areas are subject to heating, so this requiring an effort on the air cooling system. And in order to go towards high repetition rate, also from the plasma module point of view, there is a lot of work which is ongoing, in particular on the material of the capillary used, in order to find the one with particular characteristics such as high thermal conductivity, and one solution has been found in this prototype, which has been realized for the Eupraxia project, which is a 60 centimeter long Chapal capillary, for which you can find also in this paper all the details concerning the realization. So based on this improvement, which have been done in the past years and in the present year, concerning the quality of the plasma accelerated beam, there are several ambitious large-scale projects under development. So the one we are involved, the Eupraxia project, the Chinese project, and also the project which foresees a plasma injector for a light source for the Petra 4 at DESY. So depending on the application, we said the high quality is a must, and also the long-term shot-to-shot stability and reproducibility. And in particular, for the FEL requirement, what we have to look is at the energy spread, because this put a limit on the bandwidth of the FEL, and this quantity here is also related to in case of particle-driven plasma acceleration, to the separation of the driver and witness bunches, and of course is also related to the stability of the plasma source. Based on the efforts we have done in the past, several groups worldwide have succeeded to demonstrate the feasibility of using plasma accelerators for running a facility for free electron laser facility. So here in these four pictures are the four experiments from the international community demonstrating the FEL lasing using plasma accelerators. So the 27 nanometers radiation wavelength from the Chinese group, the first particle-driven the first SASE fell driven by particle-driven plasma wave field accelerator, and then following the seeded free electron laser driven by a compact laser plasma accelerator from the French group, and this from very recently from Bella. Concerning the seeded FEL demonstration, the first feasibility proof of principle has been done at Spark Lab in 2022, and where we have demonstrated to provide a stable, more stable with respect to SASE FEL laser emission, with a pulse energy increase from the 30 nanojoule in the case of SASE FEL up to 1 microjoule in the case of the seeded FEL, with an increased stability of the emission radiation as shown in these images, in these figures. So based on these strong demonstrations, the Eupraxia at Spark Lab, which is one of the two legs of the Eupraxia project, is now in a quite advanced status. We have delivered our technical design report in very few weeks ago, and this is concerning is a particle-driven plasma wave field accelerator driven by an X-band LINAC to deliver electron beams to undulator beamlines, the one called Aqua beamline in the XUV soft X-ray, and the one called Aria beamline. So for from start to end simulations, we have demonstrated that with a 1 GeV electron beam energy, we can, with a 30 picocoulomb bunch, we can provide, we can perform emission, FEL emission in the SASE regime, delivering a radiation in the water window. In the baseline is 4 nanometers, with the number of photon per pulse in the order of 10 to 11, as requested, as expected by users. So the Aqua photo beamline is shown here, which is a water window optimized for the 4 nanometer with the polarization control thanks to the Apple X undulator, and allowed and able to generate ultra short radiation pulses. The second beamline is the Aria beamline, which is based on a seeded FEL, and it is based on a high gain harmonic generation covering the VUV spectral range down to the 50 nanometer. The peculiarity of this beamline is due to the fact that the seed laser is longer than the electron bunch, and by using the electron band shaping, which are natural in a photoinjector based linear accelerator, we can control also the light pulse properties. An additional, an alternative application with respect to the free electron laser is provided by the betatron emission. Betatron radiation is produced by electrons which are oscillating in the plasma module. Was a spectrum is a synchron-like spectrum, and depending on the energy and depending on the characteristics of the electron beam, the critical energy is in the range of 210 keV, with a few tenths of femtosecond duration and a number of photons, total photons, which is ranging from the 10 to 7, 10 to 9. So betatron radiation has been used to demonstrate the possibility of use single shot XANES and EXAFs with a laser-driven betatron source, and in case of careful consideration of the noise produced during the X-ray generation, it is also possible to increase the signal to noise at the detector. So these two techniques, which are typically used in conventional light sources, are the peculiarities in case of driven by betatron source to have femtosecond to run at femtosecond scale, and this would open the possibility to pump probe experiment in extreme conditions. In addition, operating the wave field acceleration beyond the phasing, it is possible to have a much wider transverse oscillation, which is resulting in a much higher photon flux. And in this case, also, this experiment here shows, the very recent experiment here shows the possibility to increase of a factor of 10 the photon flux of the betatron source. So other recent experiments concerning betatron radiation is shown here, where betatron source has been used to probe dense matter hydrodynamics of laser-induced shock in the water jet. And as a part of the eupraxia, eupraxia in Frascati at Spark Lab facility, we are developing the eupraxia advanced photon source. Was expected parameters are shown here, and also the bunker is shown here in these in a dual operation mode. In the flame bunker, which is the bunker where the high intensity laser flame is, to perform R&D on the laser and on the components, and in the spark bunker in order to provide beam to users in order to start the very first user experiment for using the betatron radiation source at Spark Lab. Betatron emission can be also considered as a plasma-based undulator. So by considering the betatron oscillation, and also considering the amplitude, so which is based on the K parameter and the strength parameter, very much similar to the strength parameter in a conventional undulator, it is possible to think of having a plasma module in case the longitudinal electric field is let as negligible, so is set in order to not be influenced on the motion of the electron beam. Is it possible to set under some condition to set the plasma module as a plasma undulator? What is the difference? In magnetic undulators, the strength parameter K depends only on physical constants and the magnetic fields, while in the plasma focusing bubble, the strength parameter is different for each electron and depends also on the oscillating amplitude. And this would lead to an inhomogeneous broadening of the radiation spectrum. So the point is to replace this magnetic undulator with a strong focus in ion channel, for which we can set a channel where only transverse focusing field is different from zero, while the longitudinal electric field, accelerating field, is negligible. In this case, a linear focusing force produces a periodic betatron oscillation, and the key point is then perform or provide a uniform ion column. So what happens in the neutral plasma creation is done through ionization, from laser ionization. The blowout of the plasma electrons happens through a driver beam. Then the plasma electrons are expelled from the plasma region toward the neutral gas region, and this allows for a negligible restoring force, which means that in this column, no accelerating force is within the column, but only a linear restoring force is within the column. So this would lead to go towards a plasma-based undulator. So in this image, this is an image of a simulation performed with a comb-like, with a particular setting typical at Spark Lab, demonstrating that there is a possibility to generate this kind of ion column. Another application of plasma-based accelerators is given by Compton sources. For each, in case of self-aligned and synchronized ultra-high brilliance Compton sources, which have been demonstrated to be produced using a single laser beam, it is possible to generate this source with a high spectral brightness for multi-MeV electron energy, ideal for nuclear application, for instance. And there are several experiments which are ongoing recently worldwide. Another application is given by positron. So positron may be needed for future lepton colliders, for instance, and the acceleration of positron have been demonstrated also in the nonlinear regime. But in the blowout regime, some alternative, some creative solution must be considered. In particular, was proposed this solution here on the right image, where acceleration of positron has been demonstrated in a hollow plasma in order to avoid focusing force on axis. In this regard, the positron application is a flagship application in eupraxia, and here is the project and the simulations of a positron beamline designed for a 200 terawatt system, which is suitable both for laser-driven and beam-driven studies, and this would the first facility of this kind worldwide. Another application, which is probably not a natural application of a party of plasma-based accelerators, is given by cancer therapy. So laser accelerated proton beams are ultra short compared to conventional sources, and this allows for investigating this flash effect. But in this regard, there are several experiments performed at different labs which have demonstrated the beneficial effects of plasma-based accelerators, and in particular for this kind of applications on in vivo samples. And beyond flash, there are also a lot of experiments which are ongoing in order to study novel radiobiology techniques. So an eupraxia could allow also this kind of topics in the femtosecond realm. Another application for plasma-based accelerators is given by muon beams. So laser plasma accelerators can generate electron beams capable of producing GeV scale muons with some advantages with respect to over cosmic ray backgrounds. And there are several, there are some experiments which are ongoing in this regard. So in this compact directional high yield muon sources could enhance the muon imaging by reducing exposure times by order of magnitudes. Then several other applications are ongoing, ultra-fast electron diffraction, for instance, and nuclear physics. And in these two pictures are shown the two experiments which are ongoing on this particular topic. Finally, but last but not least, the plasma injector has been proposed for a light source for Petra 4. So based on the technology we have available today at this time, this is feasible, and also the simulations include realistic jitters in laser energy wavefront RF phase and laser to RF synchronization, demonstrated that this application, which is more on the technology of the overall facility, can be affordable. So I would like not to conclude with a conclusion, a conventional conclusion. I would like to conclude with this milestone from the very beginning. So from where the very beginning is not the idea, but is the demonstration of experimental demonstration of compact of the Dream Beam, so as an alternative to conventional accelerators, going on with the demonstration of the high efficiency of plasma accelerators. The quality, which has been demonstrated, so another milestone has been set in 2021 with a quality demonstration by several groups worldwide. And I would like to go towards the very first plasma-based facility, which might be the Eupraxia project. And thinking to the particle-driven plasma accelerators, the Eupraxia Spark Lab project, for which the technical design report has been published, and you can have access here. So thank you for your attention, and thanks to all the person which also not aware have been of inspiration, actually, for me, for the preparation of the talk. Thank you.
Thank you very much, Enrica, for a very nice presentation and overview of the different application of plasma-based accelerators. So let me see if there are any questions in the chat. There is one by Devdeep. He says, was there any other technique involved in transverse profile measurements, or is there any plan? Because quartz scans require multiple measurements and is invasive.
Actually, there is a direct measurement. Of course, there are several techniques to measure the emittance, the transverse emittance. One might be also let's say, kind of pepper pot, but and there have been some group which have been measured emittance by using more conventional techniques, but depending on the characteristics of this kind of beam, also other conventional techniques are not really useful or good to be used, because they could introduce some errors in the measurement. So in my opinion, the best way to measure, not to measure, but to have an indication of the quality of the beam is the FEL. So the fact that, which is an indirect measurement. So the fact that you can measure or you can produce free electron laser radiation, this is an indication that your emittance is good, because otherwise you would never laser. Of course, this is not giving an absolute value as a measure would do, but is one of the best diagnostics. So the fact that there is a FEL lasing, because of course quadruple scan is a multi-shot, and so is and the fact it is a multi-shot is not only is not the worst thing, actually, because also the transport might be an issue. So yes, there are several techniques, but for this kind of beam, probably not all the techniques can be applied for measuring emittance.
Yeah, thank you.
Thank you. Thank you, Enrica. Yeah, I just to follow up on this, because I asked this question as I saw you did mention about the betatron radiation, synchrotron radiation. So we are basically developing this optical synchrotron radiation based diagnostics techniques to measure emittance. So if that would be also possible in this case, because, as you mentioned, probably the paper pod, I mean, they are good, but then they have a limitation on the resolution side, low energy side, and then it comes the optical part of the synchrotron radiation. Or if you do the betatron as well, then you can encode that as well.
Yes, sure. Betatron, and actually betatron radiation is one method also for measuring emittance. And at Spark Lab, we have also demonstrated the emittance measurement by means of betatron radiation in the laser wave field acceleration by using the flame laser. And these allow to have an indication of the emittance in the plasma module. So, of course, there is also betatron radiation, which is one technique to be used, of course. Yeah.
Okay.
Okay, I don't see any other questions, but I just have one question. Since plasma accelerators mainly concern with miniaturization of the conventional accelerators, so what kind of, like, maybe 3 important technology challenges that you face or you see when you are trying to, miniaturize the laser in general? Is it the material? Is it the laser that is the most challenging part, or is it something else? Just a comment.
Yeah, I think that to miniaturize the overall accelerator, we have to start from the ancillary components, and a lot of work has been done in order to provide or to substitute, for instance, focusing elements with plasma lenses. Also, probably you have listened from previous seminars. There is this idea to use plasma to bend particle beams. So also bending magnets might be substituted with plasma in order to go towards a miniaturization. Concerning other parts, probably we need to the miniaturization of the overall facility is still a bit needs still investigation and a technological step in order to go towards even more compact facility. But in any case, already at this stage, we, with respect to conventional facilities, conventional acceleration-based facility, the plasma-based ones are already much shorter, much shorter than the conventional one. So if we compare the Neopraxia Spark Lab facility, which would provide a 1 GeV electron beam with accelerated with plasma, with, for instance, the Flash facility, which is providing 1 GeV in 250 meters. So probably this is already a step towards the miniaturization. Of course, in order to go a bit further, we need an important technological step.
Thank you very much. Is there any other question which anybody wants to ask? Okay, so thank you again, Enrica, for a very nice presentation. And to all of you people in the audience, please keep following the website for the updates for our next talk, and I'll see you again next month. Have a nice weekend. Bye.
Bye-bye.